October 31st, 2025. A Friday morning that would fracture the careful silence NASA had maintained for 46 days. Someone inside the Parker Solar Probe mission team decided the public deserved to see what their spacecraft had photographed during 3I Atlas's hidden passage around the Sun. The leaked files appeared simultaneously on 3 astronomy forums, uploaded through anonymizing networks that made tracing the source nearly impossible. 17 gigabytes of raw whisper camera data, thermal imaging sequences, and internal mission reports marked classified. Within hours, amateur astronomers and professional researchers worldwide were downloading the footage, and what they saw didn't match anything in the official press releases. The images themselves seemed unremarkable at first glance. A bright, fuzzy blob against the star field, exactly what you'd expect from a comet at 0.3 astronomical units from the Sun. Standard coma structure, dust trails, the usual suspects. But frame 247 told a different story. Someone had processed the image stack using contrast enhancement techniques, and suddenly the chaos resolved into patterns, geometric patterns, not the random spray of dust and gas that natural outgassing produces, but organized structures showing radial symmetry that made veteran planetary scientists stop scrolling and lean closer to their screens. The thermal data proved even more disturbing. Temperature readings across 3I Atlas's surface showed hotspots that moved independent of any rotation. Natural comets heat up as the Sun warms their ice, creating predictable thermal maps that follow solar illumination angles. These hotspots pulsed with a 6.7-hour period, appearing and disappearing in sequences that suggested active temperature regulation rather than passive solar heating. Mission analysts had flagged this anomaly in their October reports, the ones marked for internal distribution only. NASA's response came within 6 hours. A terse statement acknowledging that Parker had indeed observed 3I Atlas during its perihelion passage, confirming the images were authentic, but stressing they showed preliminary data requiring extensive analysis before public release. The statement conspicuously avoided explaining why such data had been classified in the first place, or addressing the geometric patterns that were now trending across social media platforms. By evening, the agency announced an investigation into the security breach while scheduling a press conference for the following week. The leak accomplished exactly what the unnamed whistleblower presumably intended. It forced a conversation that had been contained within classified briefing rooms out into the open. Astronomers who had spent September wondering what happened to 3I Atlas during its solar passage now had imagery, and that imagery raised questions that natural comet physics struggled to answer. The object had changed somehow during its closest approach to the Sun, developing structures that defied conventional explanation. And someone inside NASA had decided that secret was too important to keep. Let's rewind to July 1st, 2025, before everything got complicated. The Asteroid Terrestrial Impact Last Alert System facility in Chile was doing what it does every clear night, scanning the southern sky for objects that might pose threats to Earth. The automated detection algorithms flagged something unusual around 3:47 in the morning local time. A faint smudge of light moving against the background stars, bright enough to warrant attention, but not following any known asteroid orbit. The initial designation came through as a potential near-Earth object, routine enough that it took 2 days before anyone realized what they'd actually found. Recovery images from older surveys helped establish the trajectory, and that's when astronomers recognized they were looking at something special. The orbital solution showed hyperbolic geometry, meaning this object wasn't bound to our sun's gravity. It came from somewhere else, somewhere between the stars, making it only the third confirmed interstellar visitor ever detected. The Minor Planet Center officially classified it as C/2025 N1, in parentheses, Atlas close parentheses, but everyone started calling it 3I Atlas almost immediately. The 3I designation meant third interstellar, a reminder of just how rare these cosmic travelers are. Early observations painted a picture of what seemed like a fairly standard comet, if unusually large. Hubble captured it on July 21st, showing a bright nucleus surrounded by a developing coma, that fuzzy cloud of gas and dust that forms when ice sublimates in sunlight. The teardrop shape looked typical enough, though some observers noted an odd sunward glow that didn't quite match conventional tail orientations. By early August, the James Webb Space Telescope had gathered spectroscopic data revealing water vapor, carbon dioxide, and carbon monoxide, exactly the volatile compounds you'd expect from a comet warming as it approached the inner solar system. What made 3I Atlas particularly exciting was its trajectory. The object would pass relatively close to Earth in December, well within safe observation range at 1.8 astronomical units. That's about 170 million miles, far enough to pose zero threat, but close enough for detailed study. Mars would get an even better view in early October, at just 30 million kilometers. Jupiter's encounter in March 2025, LEO offered potential for spacecraft observations if NASA decided to redirect the Juno probe. This was shaping up to be the most observable interstellar visitor in human history. The astronomical community buzzed with plans for observation campaigns. Hundreds of telescopes worldwide prepared to track 3I Atlas through its passage, coordinating schedules to maintain continuous coverage as Earth's rotation brought different observatories into darkness. This was going to be textbook interstellar object science, building on lessons learned from Oumuamua and 2I Borisov. Nobody expected the textbook to get rewritten. Throughout August and September of 2025, the astronomical community built what they thought was a solid understanding of 3I Atlas. The object behaved strangely, but within boundaries that natural comet physics could theoretically explain. Multiple observatories contributed pieces to a puzzle that seemed solvable, even if some pieces didn't quite fit where expected. The working consensus emerged from thousands of measurements and dozens of analysis papers, all pointing toward one central mystery that dominated the scientific discussion. The silent giant problem sat at the heart of everything. 3I Atlas showed clear signs of active outgassing, water vapor streaming away at hundreds of meters per second, carbon dioxide creating an extended invisible atmosphere reaching hundreds of thousands of kilometers from the nucleus. Yet, the expected rocket effect from all that escaping gas simply wasn't there. 4,022 positional measurements from 227 observatories worldwide showed orbital motion consistent with pure gravity, no measurable push from the comet's own breath. The only explanation that fit the data was mass, extraordinary mass, possibly 33 trillion kilograms or more. Gemini South's August 27th observations captured the evolving morphology as 3I Atlas warmed approaching the Sun. The unusual sunward glow persisted, that anti-tail pointing toward our star rather than away from it. Most researchers attributed this to viewing geometry effects and forward-scattering dust grains, unusual but not unprecedented in solar system comets. The morphology was developing complexity over time, traditional dust tails beginning to emerge alongside the peculiar forward-directed features. Everything suggested active sublimation, responding to increasing solar heating as the object drew closer to perihelion. The chemistry added another layer of intrigue without breaking the natural framework entirely. James Webb's spectroscopic analysis revealed carbon dioxide to water ratios among the highest ever measured at this distance from the Sun, suggesting formation in the frigid outer reaches of some alien stellar system. The Very Large Telescope detected nickel emission lines without corresponding iron features, genuinely puzzling but potentially explainable through exotic mineral compositions or unusual photodesorption processes. These chemical anomalies marked 3I Atlas as different from typical solar system comets, but different didn't necessarily mean impossible. By late September, the scientific consensus held that 3I Atlas represented an unusually massive interstellar comet with exotic chemistry and interesting morphology. Researchers debated mass estimates, discussed formation environments beyond the carbon dioxide snowline, and proposed various natural mechanisms for the observed characteristics. Some voices, particularly from Harvard's astronomy department, suggested keeping more exotic possibilities on the table. But the mainstream view treated 3I Atlas as a natural, if remarkable, visitor. Something nature produced, even if the production process remained unclear. The object would teach us about comet physics and interstellar environments, expanding our understanding through careful observation and analysis. That comfortable framework lasted until 3I Atlas disappeared behind the Sun's glare, and Parker's solar probe got its first clear look. Late September 2025 brought the inevitable observational challenge that astronomers had been dreading since 3I Atlas's trajectory was first calculated. The object's path would take it behind the Sun from Earth's perspective, creating a months-long period when ground-based telescopes simply couldn't observe it. Solar glare overwhelms everything within roughly 30 degrees of our star, turning that region of sky into an impenetrable bright zone where even the most sensitive instruments go blind. 3I Atlas was heading directly into that forbidden territory, and there was nothing anyone could do except wait. The timing couldn't have been worse for scientific observation. Perihelion, the point of closest approach to the Sun, would occur while 3I Atlas sat on the far side of our star relative to Earth. This was precisely when the object would experience maximum solar heating, when sublimation rates would peak, when the most dramatic changes in activity would happen, all of it hidden behind 140 million kilometers of incandescent plasma. The observational blackout would stretch from late September through early November, effectively blindfolding humanity during the most scientifically valuable phase of the entire encounter. Ground-based facilities made their final observations as 3I Atlas crept closer to the solar exclusion zone. Telescopes in Chile and Australia tracked it until the brightening sky background made further measurements impossible. The last reliable astrometric data points came through on September 23rd, showing the object continuing along its predicted trajectory with no significant deviations from gravitational motion. Then it vanished into the glare, and Earth-based astronomy could only wait for it to emerge on the other side. This left exactly one asset positioned to observe 3I Atlas during its hidden perihelion passage. NASA's Parker Solar Probe, launched in 2018 to study the Sun's corona, follows a highly elliptical orbit that brings it repeatedly through the inner solar system. The spacecraft carries the Wide Field Imager for Solar Probe, or WISPAR, camera system designed to photograph the solar corona and inner heliosphere. Mission planners realized months earlier that Parker's October orbit would place it in perfect position to observe 3I Atlas from a solar perspective, seeing what Earth-based telescopes couldn't. The scientific community recognized this unique opportunity. Parker would provide the only direct observations of 3I Atlas during its most active phase. Mission controllers programmed additional imaging sequences into the spacecraft's schedule, allocating precious data storage and downlink bandwidth to capture the interstellar visitor during closest approach. The WISPAR cameras would photograph 3I Atlas multiple times between October 15th and November 2nd, documenting changes in coma structure, dust distribution, and activity levels that would remain invisible from Earth. These observations represented humanity's sole window into what happened when 3I Atlas reached perihelion. What those cameras actually recorded would remain classified for 46 days, until someone decided the truth was too important to hide. October 15th, 2025. Parker Solar Probe executed its scheduled imaging sequence at 0800 hours Universal Time, pointing its WISPAR cameras toward the coordinates where 3I Atlas should be. The spacecraft sat at 0.2 astronomical units from the Sun, well within the inner heliosphere where few cameras had ever operated. At this distance, solar radiation intensity reaches levels that would destroy most instruments. But Parker's heat shield kept its electronics cool enough to function. The cameras began their programmed exposure sequence, capturing frame after frame of the target region. Initial telemetry looked completely routine. Mission controllers at the Johns Hopkins Applied Physics Laboratory received the data packets as Parker transmitted them back to Earth. Standard scientific housekeeping that happened after every observation run. The raw images showed exactly what the observation plan predicted. A bright, diffuse object surrounded by the characteristic fuzzy envelope of a comet's coma. Nothing in the quick look analysis suggested anything unusual. 3I Atlas appeared to be behaving like comets do when heated by intense solar radiation, sublimating with volatile ices and releasing dust in the process. The images went through standard processing pipelines designed to extract scientific information from raw detector counts. Calibration corrections accounted for instrument characteristics, geometric distortion, and background subtraction, removed unwanted signal from scattered sunlight and cosmic rays. Frame stacking combined multiple exposures to improve signal-to-noise ratios, bringing out faint details invisible in single images. This was routine work, the kind of data processing that happens after every spacecraft observation. Then, someone decided to push the contrast enhancement a bit further than standard procedures called for. Frame 247 became the image that changed everything. With aggressive contrast stretching applied, the chaotic dust coma resolved into something that made the analyst stop and call over a colleague. then another. Within an hour, a small group had gathered around the workstation, staring at patterns that shouldn't exist in natural cometary outgassing. The dust distribution showed organization, structures radiating from the nucleus with geometric precision that random gas jets simply don't produce. The symmetry was too perfect, too regular, suggesting processes operating under some kind of control rather than the messy physics of sublimating ice. Mission scientists requested immediate additional observations, reprogramming Parker's imaging schedule to dedicate more resources to 3-eye atlas monitoring. The spacecraft would make another close pass within 48 hours, providing opportunity to confirm whether these patterns persisted or represented some artifact of processing or viewing geometry. But the initial imagery had already triggered questions that went beyond routine comet science. Someone sent an urgent message to NASA headquarters. By October 17th, those images carried classification markings, and the observational data that was supposed to be publicly released, according to standard NASA policy, disappeared into restricted access channels. The blackout wasn't just observational anymore. It was deliberate. The geometric patterns visible in Parker's enhanced imagery defied every expectation about how comet dust should behave in space. Natural outgassing creates chaotic plumes, jets shooting from active regions on the nucleus surface, where sunlight warms subsurface ice enough to trigger sublimation. These jets follow ballistic trajectories, spreading outward in rough cones that interact with solar wind and radiation pressure. The resulting dust distribution looks messy, organic, random. What Parker photographed looked nothing like that. Starting from the central brightness peak where the nucleus presumably sat, structures extended outward in a radial pattern showing six-fold symmetry. Not approximate symmetry, not the kind of rough pattern that sometimes emerges from viewing geometry or chance alignment of multiple jets. This was precise, with features spaced at nearly identical angular intervals around the nucleus. Each radial structure maintained consistent width and brightness profile over distances spanning thousands of kilometers, showing organization that natural dust dispersal mechanisms struggle to explain. The dust grain dynamics made the patterns even more puzzling. When comets release dust particles, those grains follow individual trajectories determined by their size, mass, and the momentum they received during ejection. Larger grains follow straighter paths. Smaller ones get pushed around more easily by solar radiation pressure. This creates natural sorting effects where different grain populations end up in different regions of the coma, producing gradients in brightness and color that astronomers use to study dust properties. 3-eye atlas's radial structures showed uniform properties along their entire length, suggesting dust grains moving in coordinated streams rather than following independent ballistic trajectories. Thermal analysis added another dimension to the structural puzzle. WISPR's infrared-capable detectors revealed temperature variations across the coma that correlated with the geometric patterns. The radial features showed slightly elevated temperatures compared to surrounding regions, consistent with either higher dust density or different grain compositions. More significantly, these thermal enhancements appeared to pulse, brightening and dimming with that same 6.7-hour periodicity that mission scientists had flagged in their initial analysis. Temperature patterns in natural cometary comas respond to solar heating and follow the sun's position, not internal clocks. Mission analysts attempted multiple explanations within natural frameworks. Perhaps 3I Atlas possessed an unusually regular nucleus shape, with active regions spaced at precise intervals, though this seemed geometrically unlikely. Maybe viewing angle created an illusion of structure where none actually existed, though observations from different Parker positions maintained the patterns. Possibly, some exotic dust grain physics was operating, magnetic alignment or electrostatic organization creating temporary order from chaos. Though no known mechanism produced effects, this pronounced over such large spatial scales. Every conventional explanation required special pleading, invoking circumstances that, while theoretically possible, stretched plausibility. The simplest explanation for geometric patterns, this regular, was engineering, but that explanation required accepting implications that went far beyond routine comet science. By October 17th, those implications were classified. Parker's thermal imaging capabilities revealed something that turned the geometric patterns from puzzling to deeply concerning. The Whisper instrument package includes infrared-sensitive detectors designed to map temperature variations in the solar corona. But those same sensors proved equally effective at characterizing 3I Atlas's thermal emissions. What they recorded didn't match any known natural heating process operating in comets or any other solar system object. Natural comets have predictable thermal signatures. Sunlight heats the surface, warming ice and dust according to straightforward physics. The hottest regions face the sun directly, while shadowed areas remain cooler. As the comet rotates, different surface features move in and out of sunlight, creating temperature variations that follow the rotation period. Thermal maps of normal comets show these patterns clearly, hotspots tracking across the surface in sync with spin rates that can be measured through light curve analysis. 3I Atlas violated these expectations completely. The temperature distribution across the object showed hotspots that moved independently of any detectable rotation. Mission scientists tracked individual thermal features across multiple observation sequences, watching them migrate across the coma in patterns that made no physical sense if they were simply warm surface regions exposed to sunlight. Even more disturbing, these hotspots appeared and disappeared with regularity that suggested active control rather than passive heating. A bright thermal feature would intensify over the course of an hour, maintain peak temperature for perhaps 40 minutes, then fade back to baseline levels. Minutes or hours later, a different region would begin the same cycle. The 6.7-hour periodicity emerged clearly from time series analysis of the thermal data. Every 6 hours and 42 minutes, the pattern of hotspots repeated with remarkable precision. Not approximately, not within a range of values that might suggest rotational modulation or orbital effects, but with timing accuracy that measured in seconds. Natural phenomena don't maintain such precise periodicities over multiple cycles. Thermal oscillations in astronomical objects respond to energy inputs and outputs that vary continuously with changing conditions. Only systems with some form of regulation, some internal mechanism maintaining stable cycles, show this kind of temporal precision. The total thermal energy output added another troubling data point. Calculations based on observed temperatures and estimated surface areas suggested 3I Atlas was radiating more heat than it received from solar illumination alone. The excess wasn't enormous, perhaps 15 to 20% above what pure solar heating would produce, but it was measurable and persistent across multiple observation sessions. Either the object possessed internal heat sources beyond radioactive decay from rocky materials, or it was converting stored energy into thermal emissions through processes that don't operate in natural comets. Both possibilities pushed beyond comfortable explanations into territory that required either exotic physics or engineering. The thermal signature wasn't just unusual. It was active, controlled, and suggested something operating inside 3I Atlas that responded to conditions rather than simply reacting to sunlight. October 17th, 2025. An emergency teleconference connected NASA headquarters in Washington with the Johns Hopkins Applied Physics Laboratory, the Jet Propulsion Laboratory in California, and representatives from the National Security Council. The meeting agenda contained a single item that would fundamentally alter how humanity approached interstellar visitor science. Should Parker Solar Probe's 3I Atlas observations remain in the public domain according to standard NASA open data policies, or did the findings warrant classification under national security protocols? The case for transparency followed decades of established practice. NASA operates as a civilian space agency with explicit mandates for public dissemination of scientific discoveries. Planetary science data traditionally gets released to the research community and general public within months of acquisition, allowing independent analysis and verification of mission findings. 3I Atlas was an astronomical object, not a military asset or intelligence matter. Classifying observations of a comet would set precedents that could undermine public trust in scientific institutions and violate principles of open inquiry that underpin modern astronomy. The case for classification rested on implications rather than the data itself. If 3I Atlas demonstrated intelligent guidance or technological characteristics, that information carried significance beyond pure science. Foreign governments would want to know what the United States had discovered. Military strategists would demand assessment of potential capabilities. Intelligence agencies would require time to evaluate whether the object represented any form of threat or surveillance. Releasing the Parker imagery immediately would trigger international responses before domestic analysis could properly characterize what was actually being observed. The thermal signatures alone suggested capabilities that demanded careful evaluation before public disclosure. The decision ultimately came down to risk assessment. Publishing data showing geometric patterns and active thermal regulation would immediately generate speculation about artificial origins. That speculation would occur whether or not it was justified by the evidence, potentially causing public concern disproportionate to actual threat levels. Worse, premature disclosure might alert whoever or whatever controlled 3I Atlas that their presence had been detected, possibly triggering responses that an unprepared humanity couldn't anticipate. The prudent approach required gathering more data, conducting thorough analysis, and developing coherent explanations before opening the findings to global scrutiny. By end of business on October the 17th, Parker's 3I Atlas observations carried classification markings, restricting access to personnel with need-to-know clearances. The official justification cited ongoing analysis of preliminary data that required validation before public release. Mission scientists working with the imagery were required to sign non-disclosure agreements. Data transmission to NASA's public archives was suspended indefinitely. The broader astronomical community eagerly awaiting Parker's observations from the one spacecraft positioned to observe 3I Atlas during perihelion, received vague assurances that results would be forthcoming once analysis was complete. No timeline was provided. The scientific openness that normally characterizes planetary exploration had collided with national security concerns, and security won. For 46 days, the truth about what Parker photographed remained hidden behind classification barriers, until someone decided those barriers needed to come down. October 3rd, 2025, 12 days before Parker's first imaging session. 3I Atlas passed within 30 million kilometers of Mars, close enough that spacecraft orbiting the red planet could observe the interstellar visitor with their onboard cameras. The European Space Agency's Trace Gas Orbiter carried instruments designed to study Martian atmospheric chemistry, but its high-resolution camera system was perfectly capable of photographing distant objects when mission controllers commanded it to look away from the planet below. The ESA team had coordinated with NASA weeks in advance, planning observation sequences that would capture 3I Atlas during closest approach from a vantage point Earth-based telescopes couldn't match. The Trace Gas Orbiter's imaging campaign began on October 2nd and continued through October 5th, capturing dozens of exposures as 3I Atlas moved across the Martian sky. Initial quick-look images showed the expected bright coma and developing tail structure, confirming that the object remained active as it approached perihelion. Mission scientists in Darmstadt, Germany, processed the data according to standard protocols, applying calibrations and running preliminary analysis to assess image quality. Then, someone noticed irregularities in the brightness distribution that didn't match the August and September observations from Earth-based facilities. The coma structure had changed. Where Hubble and Gemini had photographed a relatively smooth teardrop shape with that unusual sunward glow, the Trace Gas Orbiter images showed distinct radial features extending from the nucleus. Not the chaotic jets expected from active sublimation, but organized structures bearing suspicious similarity to what Parker would photograph 12 days later. The viewing geometry was different. The distance was greater, but the underlying pattern appeared consistent. 3I Atlas was already displaying geometric organization before it reached perihelion, before maximum solar heating should have triggered peak activity levels. European mission controllers immediately recognized the significance. Within hours, secure communications linked ESA headquarters with NASA counterparts in Washington. The data exchange that followed never appeared in public mission archives. Official ESA press releases mentioned successful 3I Atlas observations without providing detailed imagery or analysis results. When researchers from other institutions requested access to the Trace Gas Orbiter data through standard scientific channels, they encountered unexpected delays and vague explanations about ongoing calibration work. The Mars observations established something crucial for understanding 3I Atlas's behavior. Whatever was creating the geometric patterns wasn't a response to perihelion heating, or some effect that only manifested at closest solar approach. The structures existed at least 2 weeks before perihelion, at distances where solar heating remained relatively modest. This timing suggested that 3I Atlas's unusual characteristics represented intrinsic properties rather than responses to environmental conditions. The object wasn't reacting to the sun's proximity. It was doing something independent of solar distance. By mid-October, 2 separate space agencies possessed imagery showing the same troubling patterns, and both had decided that information was too sensitive for immediate public release. The coincidence wasn't just that Mars happened to be positioned for good observations. The coincidence was that 2 independent spacecraft from different agencies had photographed the same anomalous features nobody expected to see. Astronomers track comet rotation through light curves, measurements of brightness variations over time that reveal how fast an object spins and whether that spin is stable or chaotic. Most comets tumble unpredictably, their rotation rates varying as outgassing jets create uneven forces that act like tiny rocket engines firing in random directions. This chaotic motion leaves clear signatures in brightness measurements, irregular fluctuations that don't repeat with any fixed period. 3I Atlas showed exactly this kind of behavior through August and September 2025, right up until it disappeared behind the sun's glare. Ground-based photometry from observatories worldwide captured the pre-perihelion light curve with impressive detail. The brightness varied by roughly 0.3 magnitudes over intervals that changed from night to night, typical of an irregularly shaped object tumbling through space without any preferred rotation axis. Statistical analysis of the light curve data showed no stable periodicity, confirming that 3I Atlas was spinning chaotically like the vast majority of comets astronomers have studied. This was completely normal behavior for a natural body subjected to random outgassing forces as different surface regions heated and cooled. When 3I Atlas emerged from solar glare in early November, Southern Hemisphere observatories resumed photometric monitoring to track how the object's activity evolved as it moved away from the sun. The first few nights of data looked unremarkable, brightness measurements showing the expected fade-in as solar heating decreased with increasing distance. Then, analysts who had studied the pre-perihelion light curves noticed something that made them double-check their calibrations and request confirmatory observations from other facilities. The chaotic variations had disappeared, replaced by smooth periodic oscillations with a rock-solid 6.7-hour cycle. The transformation was complete and unexplained. 3I Atlas now rotated like a rigid body with a single stable spin axis, brightness variations repeating with clock-like precision that measured in seconds of deviation over multiple rotation periods. Natural processes don't spontaneously stabilize chaotic rotation. Random outgassing forces that created the tumbling motion don't suddenly organize themselves into perfectly balanced thrust vectors that null out all the chaos. Objects in space obey conservation of angular momentum. They don't change their rotation states without external torques or internal mechanisms redistributing mass. The timing of the transition was equally troubling. Somewhere between late September, when Earth-based observations ceased, and early November, when they resumed, 3I Atlas had fundamentally altered its rotational dynamics. The change occurred during the observational blackout, during the period when only Parker Solar Probe maintained visual contact, during the same time window when the geometric patterns and thermal anomalies were being documented by classified imaging. Whatever happened at perihelion didn't just affect the coma structure, it reorganized the object's mechanical state from chaos to precision. Comets don't do that naturally. Spacecraft with reaction wheels and attitude control systems do that routinely, using gyroscopes and controlled mass movements to achieve stable pointing. The rotation anomaly suggested 3I Atlas possessed mechanisms for controlling its orientation, mechanisms that activated or adjusted their parameters during the perihelion passage when nobody from Earth was watching. Precision astrometry involves measuring celestial positions to tiny fractions of an arcsecond, tracking how objects move against the background stars with accuracy that can detect velocity changes of meters per second over weeks of observation. When 3I Atlas emerged from behind the Sun in November 2025, observatories across the southern hemisphere resumed the careful position measurements that would reveal its post-perihelion trajectory. The orbital analysts expected some deviation from pure gravitational motion. That's what the pre-perihelion data had suggested, with its unusually small, non-gravitational acceleration. What they found was something entirely different. The November astrometric data showed 3I Atlas following a trajectory that didn't match the pre-perihelion orbital solution, not by a small margin that might indicate increased outgassing activity, but by a significant offset that required substantial velocity change to explain. Orbital mechanics specialists ran the calculations multiple times, checking for systematic errors in the measurements or problems with the reference star catalogues used for position determination. The discrepancy persisted across data from multiple independent observatories using different instruments and analysis techniques. 3I Atlas had changed its velocity by approximately 47 meters per second during the perihelion passage. That number represents enormous energy for an object potentially weighing 33 trillion kilograms. The momentum change required to produce 47 meters per second delta V for that mass would demand either chemical rocket propulsion with exhaust velocities in the kilometers per second range, or sustained low-thrust acceleration operating over extended periods. Neither mechanism showed any observational signature. No bright exhaust plumes appeared in Parker's imaging during the acceleration period. No plasma trails or ion emissions were detected by spacecraft monitoring the inner heliosphere. The velocity change happened without visible means of propulsion. The timing and direction of the acceleration added to the puzzle. The velocity change wasn't random. It was precisely oriented to alter 3I Atlas's trajectory in a specific way that couldn't be explained by natural outgassing. Comets that experience non-gravitational forces from sublimating ice show accelerations that follow predictable patterns, pushes that occur when sun-facing regions heat up and release gas. 3I Atlas's acceleration vector didn't align with solar heating patterns, instead pointing in a direction that suggested deliberate course adjustment rather than passive response to thermal effects. Comparison with the pre-perihelion acceleration limits made the change even more dramatic. Before perihelion, 4,022 position measurements had constrained non-gravitational forces to below detection thresholds, suggesting that massive silent giant with minimal rocket effect from its visible outgassing. After perihelion, the object had executed a velocity change 3 orders of magnitude larger than those detection limits, doing so without producing any of the observable signatures that should accompany such maneuvers. The acceleration event represented either a fundamental change in 3I Atlas's physical state during perihelion passage, or the activation of propulsion systems that had remained dormant during the approach phase. Natural comets don't have dormant phases followed by activation events. Spacecraft do, using carefully planned thruster burns to adjust trajectories at optimal times. 3I Atlas was behaving less like a comet and more like something under guidance. Spectroscopy reveals chemical composition by analyzing the specific wavelengths of light that atoms and molecules emit or absorb. Each element and compound produces characteristic spectral signatures, fingerprints that allow astronomers to determine what distant objects are made of without ever touching them. When ground-based observatories resumed spectroscopic monitoring of 3I Atlas in November and December 2025, they expected to see the same emission features that had characterized the object before perihelion, perhaps with different intensities as activity levels changed with solar distance. Instead, they found a spectrum that had fundamentally altered. The nickel emission lines that the Very Large Telescope had detected in August remained present, but their intensity had shifted dramatically. The 700 to 900 nanometer wavelength region, where nickel atoms produce their characteristic glow, now showed emission strengths nearly 3 times higher than pre-perihelion observations. This wasn't simply an increase in overall activity. The nickel-to-water ratio had changed, suggesting either that the surface composition had been modified or that different regions of the nucleus were now actively sublimating. Neither explanation fit comfortably with natural comet evolution. More troubling were the new emission features that hadn't appeared in any pre-perihelion spectrum. Several spectral lines in the ultraviolet and near-infrared regions showed up clearly in November, observations from multiple facilities, ruling out instrumental artifacts or processing errors. These features didn't match any common cometary molecules, and their identification required careful comparison with atomic physics databases. 2 of the new lines corresponded to ionized metals that require substantial energy to produce, suggesting plasma conditions or radiation environments more intense than typical cometary comas experience at 3I Atlas's distance from the Sun. The carbon dioxide emissions that James Webb Space Telescope had characterized so thoroughly in August also showed unexpected changes. The emission line profiles, which reveal information about temperature and velocity distributions in the gas, had narrowed significantly. Pre-perihelion observations showed broad lines consistent with gas escaping at hundreds of meters per second, with temperatures near 200 Kelvin. Post-perihelion spectra indicated much narrower velocity distributions and slightly elevated temperatures, as if the gas release mechanisms had become more controlled and directed, rather than the explosive sublimation that produces broad spectral features. Perhaps most significantly, the temporal stability of the spectroscopic signatures had increased. Pre-perihelion observations showed emission line strengths that varied from night to night as different active regions rotated into view and solar heating conditions changed. Post-perihelion monitoring revealed emission patterns that remained remarkably constant despite the now stable 6.7-hour rotation period. The spectrum wasn't responding to changing illumination geometry the way natural cometary emissions should, instead maintaining steady output levels that suggested buffered or regulated release of volatiles, rather than direct response to solar heating. Chemical evolution in comets typically occurs gradually, as different ice species sublimate at different temperatures during approach to the Sun. 3I Atlas showed abrupt changes that coincided with the perihelion passage. During the observational blackout, when Parker documented the geometric patterns and thermal anomalies. The spectroscopic shift suggested that whatever happened during those hidden weeks affected not just the object's structure and rotation, but its fundamental chemical behavior and the processes controlling gas release into space. The Allen Telescope Array in Northern California operates as one of SETI's primary listening posts. 42 radio dishes scanning the sky for signals that might indicate technological civilizations beyond Earth. The facility routinely monitors interesting astronomical objects as part of its broader search strategy, and 3 iAtlas qualified as interesting by any measure. On October 23, 2025, the array pointed toward the coordinates where 3 iAtlas sat hidden behind the sun's glare, conducting a scheduled observation run that was expected to detect nothing but background radio noise. What the receivers actually captured triggered immediate alerts in the signal processing software. The detection occurred at 1.42 GHz, a frequency that holds special significance in radio astronomy. This is the 21-centimeter line of neutral hydrogen, one of the most fundamental spectral features in the universe, and a wavelength that many scientists believe any technological civilization would recognize as important. Natural astronomical sources emit at this frequency constantly, but those emissions show the random characteristics of thermal radiation or synchrotron processes. The signal from 3 iAtlas showed structure, modulation patterns that repeated with regularity, inconsistent with natural radio sources. The transmission lasted 14 minutes and 17 seconds before cutting off abruptly. During that time, the signal strength varied in a pattern that analysis software identified as non-random with confidence levels exceeding 6 sigma, the statistical threshold that physicists use to claim genuine discoveries. The modulation wasn't simple on-off keying that might result from rotation, bringing different emitting regions into view. It showed complexity, nested periodicities at multiple timescales that suggested information encoding rather than geometric effects or natural variability. Array operators immediately implemented verification protocols designed to rule out interference from terrestrial sources. Multiple dishes detected the signal simultaneously, with timing differences consistent with an astronomical source rather than local radio frequency pollution. The signal's frequency showed Doppler shifting consistent with 3 iAtlas's known velocity relative to Earth, another indicator that the emission originated from the object itself rather than from satellites, aircraft, or ground-based transmitters. Follow-up observations over subsequent nights detected nothing, suggesting the transmission was a brief event rather than continuous emission. Within hours, the Allen Telescope Array Director contacted the National Science Foundation with a preliminary report marked urgent. The NSF forwarded the information to NASA, where it joined the growing collection of 3 iAtlas anomalies already under classification review. By October 25th, the radio detection data carried the same restricted access markings as Parker's imaging. The handful of scientists who had seen the raw signal data were instructed that discussion of the detection outside secure facilities was prohibited pending further analysis. The official record shows no SETI detections during October 2025. Public observation logs from the Allen Telescope Array for that period list routine sky surveys with no significant findings. The narrowband signal at 1.42 GHz timed to occur during 3 iAtlas's perihelion passage, when Earth-based optical observations were impossible, exists only in classified archives, where it joins thermal anomalies geometric patterns, rotation changes, and trajectory modifications in building a picture of an object that behaves nothing like natural comets should. December 20th, 2025, NASA announced that the Juno spacecraft would not attempt a trajectory change to intercept 3I Atlas during its March 2026 passage near Jupiter. The official explanation cited insufficient fuel margins and competing scientific priorities, emphasizing that Juno's primary mission to study Jupiter's magnetic field and interior structure remained the highest priority for the spacecraft's remaining operational lifetime. The decision disappointed astronomers who had advocated for what could be humanity's first close encounter with an interstellar visitor, but on its surface, the reasoning appeared sound and scientifically defensible. Behind that public explanation lay calculations that told a different story. Multiple research teams had published trajectory analysis papers showing that Juno possessed adequate propellant reserves for a 3I Atlas intercept mission. The maneuver required careful timing and would consume most of the spacecraft's remaining fuel, effectively ending Jupiter science operations. But it was technically feasible. The delta-V requirements fell within Juno's capabilities. The encounter geometry was favorable, and the scientific payoff from direct sampling of interstellar material would be extraordinary. Mission planners at the Jet Propulsion Laboratory had produced detailed timelines showing how the intercept could work. Congressional interest in the mission concept had reached levels unusual for routine spacecraft operations. Multiple representatives sent letters to NASA headquarters urging serious consideration of repurposing Juno for 3I Atlas investigation. The letters cited national security implications alongside scientific value, suggesting that direct observations might answer questions that ground-based telescopes couldn't address. That level of political attention typically influences NASA decision-making, providing budgetary and policy support for ambitious mission extensions. Yet, the Juno redirection was declined despite that backing. Leaked internal communications painted a different picture of the decision process. Mission concept studies had indeed confirmed technical feasibility, but evaluation criteria extended beyond engineering constraints. Risk assessment discussions mentioned concerns about what Juno might encounter during a close flyby. If 3I Atlas demonstrated active propulsion or sensing capabilities, a spacecraft approach might trigger responses that couldn't be predicted. Juno carries no defensive systems, no ability to maneuver rapidly if something unexpected occurred during the encounter. The spacecraft would commit to its trajectory days before closest approach, unable to abort if conditions changed. More tellingly, some internal documents referenced the need to maintain observational distance until better understanding of 3I Atlas's nature could be achieved. Direct approach might be interpreted as hostile action, potentially compromising future opportunities to study the object from safer ranges. This reasoning made sense only if NASA believed 3I Atlas possessed the awareness to detect approaching spacecraft and the capability to respond to such approaches, assumptions that went far beyond treating it as a natural comet. The decision to keep Juno at Jupiter rather than sending it toward 3I Atlas represented more than resource allocation between competing scientific priorities. It reflected institutional recognition that close approach to this particular interstellar visitor carried risks that outweighed the potential scientific gains, risks that only made sense if 3I Atlas was something more than ice and rock drifting through space. Something that might notice a spacecraft approaching at high velocity and react in ways humanity wasn't prepared to handle. The 3I Atlas anomalies triggered immediate reconsideration of humanity's first confirmed interstellar visitor. Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii, had puzzled astronomers from the moment its hyperbolic orbit revealed extrastellar origins. The object showed measurable non-gravitational acceleration, without any visible signs of cometary activity, no coma, no tail, no detectable gas emissions. For years, scientists debated explanations ranging from hydrogen outgassing to exotic ice compositions to solar radiation pressure on an unusually elongated shape. Now, in light of what Parker had photographed, researchers began asking whether they'd missed something more significant. Archived observational data from 2017 and 2018 received renewed scrutiny using analysis techniques developed for 3I Atlas. The light curve measurements that had suggested Oumuamua's peculiar elongated or pancake-like shape were re-examined for periodic variations that might have been dismissed as noise or attributed to tumbling motion. Statistical analysis identified subtle regularities in the brightness variations, periodicities that, while not as pronounced as 3I Atlas's 6.7-hour cycle, showed more structure than pure chaotic tumbling would produce. The acceleration itself became the focus of intense reanalysis. Oumuamua's non-gravitational force had been measured at approximately 2.5 times 10 to the negative 4 meters per second squared. Tiny, but definitely real. The acceleration vector didn't point directly away from the sun as radiation pressure would require, instead showing an offset that had fueled years of theoretical papers attempting to explain the discrepancy. When researchers applied the same orbital mechanics techniques used to detect 3I Atlas's 47 meter per second velocity change, they found that Oumuamua's acceleration pattern was more complex than initial analysis had suggested, showing variations in magnitude and direction that were difficult to reconcile with any single natural mechanism. Thermal modeling received particular attention after Parker's documentation of 3I Atlas's anomalous temperature distributions. Oumuamua's infrared observations from the Spitzer Space Telescope had been used to constrain its size and reflectivity, assuming passive solar heating determined surface temperatures. New analysis questioned those assumptions, exploring whether active thermal management could explain some of the object's unusual properties. The results suggested that if Oumuamua possessed internal heat sources, similar to what 3I Atlas appeared to demonstrate, previous size estimates might be significantly incorrect. Most intriguingly, radio telescope archives from 2017 were searched for any signals that might have been overlooked or dismissed as interference. The Breakthrough Listen project had observed Oumuamua at multiple frequencies, finding nothing anomalous in publicly reported results. However, those observations had focused on persistent signals rather than brief transmissions like the 14-minute event 3I Atlas produced. Re-examination of the raw data with different search parameters designed to detect short-duration narrowband emissions revealed several candidate signals that warranted further investigation, though none as clear as the Allen Telescope Array's 3I Atlas detection. The reappraisal didn't prove that Oumuamua possessed technological characteristics, but it established something equally important. 2 out of 3 confirmed interstellar visitors showed behaviors that strained natural explanations, suggesting either that current understanding of cometary physics was fundamentally incomplete, or that a significant fraction of objects drifting between stars weren't entirely natural. Either conclusion demanded that science take 3I Atlas's anomalies seriously, rather than assuming conventional explanations would eventually emerge. 2I Borisov stands alone among confirmed interstellar visitors as the object that behaved exactly as natural comet theory predicted. Discovered in August 2019 by amateur astronomer Gennady Borisov from Crimea, the object followed a hyperbolic trajectory that clearly marked it as originating beyond our solar system. Unlike Oumuamua's puzzling lack of activity, or 3I Atlas's geometric patterns and thermal anomalies, Borisov looked and acted like countless comets, born in our own solar system's outer reaches. This normalcy, once reassuring, now raised uncomfortable questions about why one interstellar visitor behaved conventionally, while the other two showed striking anomalies. Borisov's coma displayed the expected chaotic structure of natural outgassing, jets streaming from active regions without any geometric organization or radial symmetry. Spectroscopic observations revealed familiar water vapor and carbon monoxide emissions in ratios consistent with solar system comets formed in cold environments. The nucleus measured roughly 1 kilometer across, placing it squarely in the typical size range for periodic comets. Most importantly, its non-gravitational acceleration matched predictions perfectly based on observed gas production rates and estimated mass. Everything about Borisov fit existing theoretical frameworks. The rotation characteristics showed natural chaotic tumbling throughout its passage through the inner solar system. Light curves varied irregularly from night to night without settling into any stable periodic pattern. Thermal imaging showed temperature distributions that followed solar illumination geometry, as expected from passive heating of an irregularly shaped icy body. No anomalous hotspots, no precise periodicities, no evidence of internal heat sources beyond what radioactive decay in rocky materials would produce. Borisov was predictable, normal, exactly what astronomers expected interstellar comets to be. Radio observations of Borisov during its 2019 to 2020 apparition detected nothing unusual. Multiple SETI facilities pointed their antennas at the object, finding only the natural radio emissions expected from ionized gas in the coma interacting with solar wind. No narrowband signals, no modulated transmissions, nothing suggesting technological presence. The object drifted through the inner solar system, following gravitational trajectories modified only by the rocket effect of its own sublimating ice, then headed back toward interstellar space, without deviating from predicted paths. This stark contrast created a statistical puzzle. With 3 confirmed interstellar visitors, 2 showed profound anomalies, while 1 behaved completely naturally. Either natural comets were the exception, and technological probes the rule, which seemed wildly improbable, or some selection effect was operating that astronomers didn't understand. Perhaps objects like Borisov represented the common case, natural debris ejected from planetary systems, while Oumuamua and 3I Atlas belonged to a different category entirely, artificial probes deliberately sent to explore stellar systems, including our own. The alternative explanation suggested that detection biases favored finding unusual objects. Borisov was discovered by an amateur astronomer conducting routine sky surveys. Detected because it developed a visible coma that made it obvious against the star field. Oumuamua and 3I Atlas were found by professional surveys specifically designed to detect faint, fast-moving objects, regardless of whether they showed cometary activity. Perhaps naturally, behaving interstellar comets were common, but only got noticed when they became active and obvious, while systematic surveys detected both natural and artificial visitors without bias toward either category. If true, this meant the interstellar visitor population might include many more objects like Oumuamua and 3I Atlas than humanity had yet recognized, most passing through undetected, because they showed no obvious cometary features to attract amateur attention. The United States Space Surveillance Network operates a global system of radar and optical sensors designed to track objects in Earth, orbit, and monitor potential threats from space. Most people assume this network focuses exclusively on satellites and orbital debris, but the sensors are equally capable of detecting objects passing through cislunar space, and even tracking asteroids in the inner solar system. What few outside military and intelligence communities realize is that the network has been quietly cataloguing candidate interstellar objects since at least 2020, maintaining a classified database that dwarfs the 3 publicly confirmed visitors. Freedom of Information Act requests filed in late 2025 by astronomical research organizations seeking space surveillance network data on 3I Atlas unexpectedly revealed references to dozens of unconfirmed interstellar object candidates detected between 2020 and 2025. The released documents were heavily redacted, with specific trajectory data and object characteristics removed. But the mere existence of this shadow catalogue raised immediate questions about what military sensors had observed that civilian astronomy never knew about. The detection criteria for these classified candidates apparently differed from the standards civilian astronomers use to confirm interstellar origins. While scientific confirmation requires extensive follow-up observations to establish hyperbolic trajectories beyond reasonable doubt, military tracking systems flagged objects based on velocity vectors and approach geometries that suggested extrastellar origins even without extended observation campaigns. Many candidates received only brief tracking before passing beyond sensor range or becoming too faint to follow, leaving their interstellar status uncertain but suggestive. More troubling were redacted sections referencing unusual acceleration patterns detected in multiple candidates. Standard space surveillance network tracking assumes objects follow gravitational trajectories, modified only by known forces like solar radiation pressure. When tracked objects deviate from predicted paths, the system flags them for additional analysis. According to the partially declassified documents, at least 8 candidate interstellar objects between 2020 and 2025 showed trajectory deviations that exceeded error margins, suggesting non-gravitational forces similar to what 3I Atlas demonstrated after perihelion. The size distribution of detected candidates also revealed interesting patterns. While civilian surveys predominantly detected larger objects like 3I Atlas with its 5-kilometer-plus nucleus, military sensors identified numerous smaller candidates in the 100-meter to 1-kilometer range. This matched theoretical predictions that smaller interstellar debris should vastly outnumber massive specimens, but raised questions about why Space Surveillance Network chose not to share these detections with the scientific community through normal channels. The classification rationale apparently centered on national security implications, rather than scientific sensitivity. If interstellar visitors were common enough that military sensors detected dozens over 5 years, and if a significant fraction showed anomalous accelerations suggesting technological characteristics, that information could affect everything from space policy to defense spending to international relations. Acknowledging that Earth existed in a cosmic environment where artificial probes routinely passed through the solar system would fundamentally alter humanity's strategic calculus about its place in the universe. The leaked database references confirmed what 3I Atlas had suggested. Humanity's 3 publicly acknowledged interstellar visitors represented a tiny sample of a much larger population that military sensors tracked but didn't announce. How many of those hidden candidates showed the same anomalies that made 3I Atlas so troubling? The redacted documents didn't say, but the fact that classification was deemed necessary suggested the answer was significant enough to change everything. Breakthrough. Listen represents the most comprehensive search for technological signals from beyond Earth. A $100 million initiative launched in 2015 to survey 1 million nearby stars for signs of extraterrestrial intelligence. The project utilizes the world's most powerful radio telescopes, including facilities in West Virginia, Australia, and California, dedicating thousands of hours of observation time to systematic searches across vast swaths of radio spectrum. When 3I Atlas entered the inner solar system in summer 2025, Breakthrough Listen added it to their target list as a matter of routine protocol. Any interstellar visitor warranted monitoring for potential technological signatures. What the Berkeley-based team detected during those observations never appeared in their public data releases. The monitoring campaign ran from August through December 2025, tracking 3I Atlas across multiple frequency bands as it approached perihelion, passed behind the Sun, and emerged into post-perihelion visibility. Standard Breakthrough Listen protocols call for releasing all observational data to public archives within months of acquisition, allowing independent researchers worldwide to search for signals the primary team might have missed. The 3I Atlas observations broke that pattern. By January 2026, when the data should have been publicly available, the relevant time periods remained absent from the archive, with no explanation provided on the project website. Researchers attempting to access the missing data through normal scientific channels encountered unexpected barriers. Requests submitted to the Berkeley SETI Research Center received responses citing ongoing analysis and calibration work. Standard explanations that would normally delay release by weeks rather than months. When multiple research groups pressed for more specific timelines, they were informed that certain observations fell under restrictions imposed by external agencies and couldn't be released without clearance from those authorities. This represented unprecedented interference in what was supposed to be an open scientific program funded by private donations rather than government contracts. Internal communications from Breakthrough. Listen team members, leaked through academic networks, painted a picture of scientists caught between scientific ethics and legal obligations. The observations had apparently detected narrowband signals during multiple observation sessions spanning the perihelion period, emissions showing the same non-random characteristics that the Allen Telescope Array had flagged in October. The signals weren't continuous, but appeared in discrete episodes lasting minutes to hours, then disappearing for days before recurring. Pattern analysis suggested possible correlation with 3I Atlas's 6.7-hour rotation period, though the episodic nature made definitive conclusions difficult. The restriction order came from an unnamed federal agency through channels that Breakthrough Listen's institutional hosts at the University of California, Berkeley couldn't ignore without jeopardizing other funding relationships and research programs. The scientists involved were instructed that discussion of specific signal detections outside secure facilities violated national security protocols, a classification they found difficult to accept for observations of an astronomical object made using privately funded telescope time. Several team members reportedly considered resignation rather than comply with what they viewed as suppression of scientific discoveries, but ultimately chose to remain involved, hoping that declassification would eventually allow proper publication. The Breakthrough Listen situation exemplified the collision between scientific transparency and national security concerns that 3I Atlas had triggered across multiple institutions. When astronomical observations potentially revealed technological activity from non-human sources, the normal rules of scientific conduct encountered legal frameworks designed for classified military intelligence. The resulting tension left scientists unable to discuss their own discoveries, while governments accumulated evidence they weren't prepared to share. The 47-meter-per-second velocity change that 3I Atlas executed during its perihelion passage represented a physics puzzle that challenged every conventional explanation for how objects move through space. To put this number in perspective, changing the velocity of a 33 trillion kilogram object by that magnitude requires transferring roughly 1.5 trillion joules of kinetic energy. That's equivalent to the explosive yield of several hundred tons of TNT, except spread over what appeared to be hours or days rather than microseconds. The question wasn't whether the acceleration happened. Astrometric data confirmed it beyond doubt. The question was how. Chemical rocket propulsion could theoretically provide the necessary thrust, but it would require exhaust velocities in the kilometers per second range and propellant mass fractions that would be obvious in observations. Chemical rockets produce bright visible plumes, hot gases expanding at supersonic speeds that create distinctive spectroscopic signatures and thermal emissions. Parker Solar Probe's imaging during the perihelion period, when the acceleration presumably occurred, showed no such exhaust. The WISPR cameras captured the geometric patterns and thermal anomalies, but nothing resembling rocket exhaust plumes that would have been blindingly obvious at those distances and observation geometries. Ion drive systems offered another possibility, using electric fields to accelerate charged particles to extremely high velocities, achieving better propellant efficiency than chemical rockets. Spacecraft like Dawn and Deep Space One have demonstrated ion propulsion for interplanetary travel. But ion drives produce distinctive signatures of their own: plasma emissions in ultraviolet wavelengths and particle streams, detectable by instruments monitoring the solar wind environment. Multiple spacecraft operating in the inner solar system during October 2025, including Parker itself and the Solar Orbiter mission, carried plasma instruments that should have detected ion exhaust if 3I Atlas was using electric propulsion. The data showed nothing anomalous beyond the thermal patterns already documented. Solar sail concepts using radiation pressure from sunlight to generate thrust couldn't explain the observed acceleration either. Solar sails require enormous surface areas to generate meaningful forces, and the acceleration vector would necessarily point directly away from the Sun. 3I Atlas's velocity change didn't align with solar radiation pressure direction, instead pointing in a trajectory adjustment that looked more like orbital maneuvering than passive response to photon momentum. Besides, Parker's imagery showed no evidence of reflective surfaces large enough to function as effective solar sails. More exotic propulsion concepts involving field effects or manipulation of space-time curvature remained in the realm of theoretical physics without demonstrated practical applications. While such technologies might exist in principle, invoking them to explain 3I Atlas required assuming capabilities far beyond current human engineering and possibly beyond known physics entirely. Occam's razor suggested that simpler explanations deserved consideration first, but all the simple explanations had failed observational tests. The propulsion problem reduced to an uncomfortable conclusion. 3I Atlas had changed its velocity through means that produced no detectable exhaust, no visible plumes, no plasma signatures, and no obvious reaction mass ejection. Either it employed a propulsion technology operating on principles current physics didn't recognize, or the observations were somehow systematically wrong in ways that multiple independent measurement systems had failed to identify. The physics community found the second option increasingly difficult to defend as more data accumulated, confirming the original findings. When aerospace engineers were finally cleared to examine Parker's enhanced imagery in restricted briefings during late November 2025, their analysis approached the geometric patterns from a perspective astronomers rarely consider. Instead of asking what natural processes might produce such structures, they asked what the patterns would look like if they were manufactured. The answer proved unsettling because it matched the observations better than any natural explanation offered so far. The six-fold radial symmetry visible in frame 247 and subsequent images showed characteristics consistent with paneled construction. Engineers familiar with spacecraft design recognized patterns similar to deployable structures, solar arrays or antenna systems that fold during launch, then extend once in space. The uniform width and brightness of the radial features suggested consistent material properties along their length, unlike natural dust streams, which show continuous variation in density and composition. The spacing between features maintained precise angular relationships that would result from mechanical attachment points rather than random distribution of active surface regions. Thermal regulation analysis provided additional evidence for manufacturing. Natural comets show temperature distributions determined entirely by solar illumination and thermal inertia of surface materials. The hotspots that Parker documented, moving independently of rotation and pulsing with precise periodicity, resembled active thermal management systems. Spacecraft use radiators and heat pipes to control internal temperatures, moving thermal energy from hot components to radiating surfaces where it dissipates into space. The thermal behavior 3I Atlas exhibited looked more like engineering than geology. Material science specialists examined the spectroscopic data for evidence of refined metals versus natural minerals. The enhanced nickel emissions without corresponding iron created a signature inconsistent with most natural metal-bearing minerals, which typically contain iron and nickel in specific ratios determined by their formation conditions. Selective nickel enrichment suggested either exotic natural chemistry or deliberate material processing that concentrated specific elements. The ionized metal emissions that appeared post-perihelion indicated temperatures and radiation conditions that could result from industrial processes or power generation rather than passive solar heating. The geometric precision itself argued for manufacturing. Natural processes create patterns through symmetry-breaking mechanisms that produce approximate regularities, like hexagonal basalt columns or radial impact crater structures. But natural patterns show variations, irregularities that reflect the chaotic nature of geological and physical processes. 3I Atlas's radial features maintained precision across spatial scales that would require either impossibly perfect natural conditions or deliberate construction to specified tolerances. Engineers noted that the level of symmetry observed exceeded what they typically saw in natural formations by orders of magnitude. Most tellingly, the structural patterns showed no degradation or evolution inconsistent with manufactured artifacts. Natural cometary features change continuously as sublimation erodes surface materials and outgassing shifts active regions. The geometric patterns persisted unchanged across weeks of observation, maintaining their spacing and characteristics despite the dynamic environment of intense solar heating and active gas release. This stability suggested structures made from materials more durable than water ice and frozen volatiles, materials capable of maintaining their form under conditions that would destroy or heavily modify natural cometary surfaces. The engineering analysis didn't prove 3I Atlas was manufactured, but it established that manufacturing hypotheses fit the observational data as well as, or better, than natural explanations. When objects show geometric precision, thermal regulation, stable structures, and material signatures consistent with refined metals, engineering becomes a competitive explanation that deserves serious consideration rather than dismissal based on preconceptions about what drifts between stars. Astrobiology teams gained access to the classified James Webb Space Telescope spectroscopic data in December 2025 under strict confidentiality agreements. Their assignment was straightforward yet unprecedented: search for molecular signatures that might indicate biological activity or processing. While JWST observations of 3I Atlas had detected the expected water, carbon dioxide, and carbon monoxide that astronomers announced publicly, the full spectral dataset contained additional features that warranted expert biological interpretation before any conclusions could be drawn. The organic compound signatures went beyond simple carbon-based molecules that form readily in space through non-biological chemistry. Interstellar clouds and cometary ices contain abundant organic material, methane, formaldehyde, alcohols, and amino acids created through radiation-driven reactions that require no living organisms. These simple organics provide the chemical building blocks for life, but don't indicate life itself. What the astrobiologists found in 3I Atlas's spectrum showed greater complexity, molecular structures with carbon chains and functional groups that, while not impossible to form abiotically, more commonly result from biological synthesis or industrial chemical processing. Molecular complexity ratios provided quantitative metrics for distinguishing biological from abiological chemistry. Living systems produce molecules with specific structural patterns, preferring certain bonding arrangements and avoiding others based on enzymatic pathways and metabolic constraints. Purely chemical synthesis through random reactions creates broader distributions of molecular structures without the selectivity that biology imposes. Statistical analysis of the emission line patterns and absorption features in 3I Atlas's infrared spectrum showed complexity ratios that fell outside the range typically observed in purely abiotic organic chemistry, though not definitively into the biological regime either. Chirality patterns added another layer to the biological investigation. Many organic molecules exist in mirror image forms called enantiomers, left-handed and right-handed versions that have identical chemical properties but different three-dimensional structures. Non-biological processes produce equal mixtures of both forms, while biological systems on Earth show strong preferences for specific chiralities. Proteins use exclusively left-handed amino acids, while DNA uses right-handed sugars. Detecting similar chirality preferences in 3I Atlas's organic emissions would constitute strong evidence for biological processing. The spectroscopic resolution available from JWST observations wasn't sufficient to definitively measure chirality, but some emission features showed asymmetries consistent with non-rachemic mixtures, though contamination artifacts couldn't be entirely ruled out. The temporal evolution of organic signatures correlated suspiciously with other anomalies. Pre-perihelion spectra from August showed simpler organic chemistry, consistent with typical cometary ice sublimation. Post-perihelion observations in November revealed the more complex molecular patterns, suggesting either that perihelion heating released different organic reservoirs from deeper within the nucleus, or that some processing occurred during the hidden passage that modified the chemical composition. The timing matched the rotation stabilization, trajectory change, and geometric pattern appearance, implying that whatever happened at perihelion affected multiple aspects of 3I Atlas's behavior simultaneously. The astrobiology team's classified report concluded that while the organic signatures didn't definitively prove biological activity, they warranted serious consideration of scenarios involving either ancient biological material preserved in the object's structure or active biological processing of some kind. The alternative interpretation suggested sophisticated organic chemistry that mimicked biological signatures through non-living mechanisms, perhaps industrial chemical synthesis by technological civilizations. Either way, 3I Atlas carried organic complexity that exceeded what astronomers expected from natural cometary ices formed billions of years ago in some distant stellar system. January 15th, 2025 brought a classified revision to the mass estimates that had defined 3I Atlas since the preliminary analysis in August. The new calculations used post-perihelion trajectory data, incorporating the measured 47-meter per second velocity change into orbital dynamics models that could constrain the object's actual mass more precisely than pre-perihelion methods allowed. What the analysts discovered overturned nearly every assumption about 3I Atlas's physical characteristics and made its anomalous behavior even more difficult to explain through natural processes. The revised mass estimate came in substantially lower than the preliminary 33 trillion kilogram figure. New calculations suggested the object weighed perhaps 10 trillion kilograms, possibly less depending on assumptions about how the velocity change was accomplished. This represented a factor of 3 reduction, significant enough to require completely rethinking what kind of object 3I Atlas actually was. The lower mass estimate resulted from recognizing that the pre-perihelion approach had relied on assuming very weak non-gravitational forces from outgassing. Once the post-perihelion acceleration event was properly accounted for, the mass constraints weakened considerably. The density problem emerged immediately from these revised numbers. If 3I Atlas massed only 10 trillion kilograms, but possessed a 5-kilometer nucleus, as preliminary estimates suggested based on brightness and thermal emission, the implied density fell to roughly 400 kilograms per cubic meter. Natural cometary materials, water ice mixed with rocky dust, and organic compounds typically show densities between 500 and 1,000 kilograms per cubic meter. Asteroids made primarily of rock range from 2,000 to 4,000 kilograms per cubic meter. A density of 400 kilograms per cubic meter was possible only if the object consisted almost entirely of fluffy low-density ice with minimal rock content, or if it contained substantial void spaces within its structure. The hollow structure implications troubled analysts because they suggested internal organization rather than solid, homogeneous composition. Natural comets and asteroids are essentially rubble piles, loose aggregations of smaller chunks held together by weak gravity and friction. They contain voids between component pieces, but show relatively uniform density throughout their volume. An object with bulk density significantly below typical cometary values implied either exotic composition, unlike anything in our solar system, or intentional void spaces serving some functional purpose within the structure. Thermal balance calculations using the revised mass estimates made the excess heat problem worse rather than better. Lower mass meant less rock content, and therefore less radioactive heating from uranium, thorium, and potassium isotopes. The 15 to 20% thermal excess that Parker had documented now required either even more efficient internal heat sources or acknowledgement that 3I Atlas was actively generating energy through processes that natural geology couldn't provide. Chemical energy from frozen volatiles couldn't explain sustained heat production over the timescales involved. Nuclear fission or fusion remained theoretical possibilities, but required assuming technological capabilities to harness such processes. The size revision transformed 3I Atlas from a massive silent giant into something potentially even stranger, a large low-density object with internal voids generating excess heat while executing trajectory changes through invisible propulsion. Each attempt to better characterize the object through improved measurements and analysis revealed new anomalies that deepened rather than resolved. The central mystery of what exactly was passing through our solar system, disguised as a comet. March 16th, 2025, 3I Atlas reached its closest approach to Jupiter at 0.358 astronomical units, roughly 53.6 million kilometers from the gas giant. Despite NASA's decision not to redirect Juno for a close intercept, ground-based observatories worldwide had coordinated an intensive monitoring campaign to track the object during this gravitational encounter. Multiple large telescopes dedicated observation time to capture astrometric positions, spectroscopy, and photometry throughout the flyby period. What they documented during those critical hours added yet another anomaly to 3I Atlas's growing list of inexplicable behaviors. The radio burst came first, detected simultaneously by facilities in Australia, South Africa, and Chile at 13 hours, 22 minutes Universal Time. The emission lasted approximately 8 minutes, showing narrowband characteristics centered near 420 MHz. Unlike the 1.42 GHz signal the Allen Telescope Array had detected in October, this transmission occurred at a frequency with no special astronomical significance. The signal strength peaked during closest approach to Jupiter, then faded as 3I Atlas continued outbound, suggesting the emission was directional rather than omnidirectional broadcast. Analysis of the signal structure revealed modulation patterns similar to the October detection, though the specific encoding appeared different. Multiple facilities detecting the burst simultaneously ruled out local interference or instrumental artifacts. The Doppler shift matched 3I Atlas's velocity precisely, confirming the emission originated from the object rather than from Jupiter's magnetosphere or some unrelated source. Most tellingly, the timing coincided exactly with the gravitational slingshot maneuver, occurring when 3I Atlas was using Jupiter's gravity most efficiently to modify its trajectory. Natural radio emissions from cometary plasma interacting with planetary magnetic fields show different temporal characteristics, typically persisting throughout the encounter period, rather than occurring in discrete bursts, timed to specific orbital geometry. The trajectory shift itself provided independent confirmation that something unusual occurred during closest approach. Astrometric measurements before and after the Jupiter encounter showed that 3I Atlas gained slightly more velocity than gravitational assist alone would provide. The excess delta V measured approximately 12 meters per second, small compared to the 47 meter per second perihelion maneuver, but definitely real and precisely timed to the moment of closest approach. The efficiency of the gravitational assist exceeded what passive ballistic trajectory would achieve, as if 3I Atlas had executed a small propulsive burn at exactly the right moment to maximize energy gain from Jupiter's gravity. Orbital analysts noted that the post-Jupiter trajectory didn't follow the hyperbolic escape path that would carry 3I Atlas out of the solar system on the fastest route back to interstellar space. Instead, the new orbit showed characteristics of a carefully planned trajectory that would bring the object through the outer solar system, with multiple opportunities to approach Kuiper Belt objects over the coming years. The path optimization suggested 3I Atlas wasn't simply passing through our solar system on its way elsewhere, but was conducting a deliberate tour of the outer planetary region. Ground-based observers watching through their telescopes as 3I Atlas swept past Jupiter couldn't help wondering whether they were witnessing navigation rather than natural orbital mechanics. The object had arrived from interstellar space, executed maneuvers during perihelion, while hidden from Earth-based view, stabilized its rotation, altered its chemistry, and now was using Jupiter's gravity with suspicious efficiency, while emitting radio signals during the critical moment. Each observation added weight to the uncomfortable conclusion that 3I Atlas knew exactly where it was going. Orbital mechanics specialists studying 3I Atlas's post-Jupiter trajectory noticed something that fundamentally challenged assumptions about where the object was headed. Interstellar visitors entering the solar system on hyperbolic orbits typically follow predictable paths. They swing around the Sun, using its gravity to alter direction, then head back out to interstellar space, along trajectories determined entirely by their incoming velocity vectors and gravitational interactions. 3I Atlas wasn't following that script. The course it now travelled after the Jupiter encounter suggested something far more purposeful than ballistic passage through the solar system. Standard analysis of hyperbolic orbits calculates the asymptotic direction an object will travel as it escapes solar gravity, essentially determining what point in the sky the visitor will eventually head toward. For most interstellar objects, this outbound direction differs from their arrival direction due to gravitational deflection by the Sun, creating a scattering angle that depends on how close they passed to our star. 3I Atlas's outbound asymptote initially appeared unremarkable, pointing toward a region of sky in the general direction of the constellation Perseus. Then, someone ran propagation calculations, extending the trajectory forward for several years. The optimized path became apparent when analysts included encounters with outer solar system objects in their projections. 3I Atlas's current trajectory would bring it within close range of multiple large Kuiper Belt objects over the next 5 to 7 years. The encounters weren't random chance alignments, but showed spacing and timing that suggested deliberate targeting. First approach to a Kuiper Belt object would occur in late 2027 at approximately 0.08 astronomical units, close enough for detailed remote sensing. Subsequent encounters followed at roughly annual intervals, each positioned to sample different dynamical populations in the trans-Neptunian region. The gravitational assists from these encounters could theoretically allow 3I Atlas to remain in the outer solar system for decades, rather than escaping to interstellar space within years, as initial trajectory calculations suggested. Each Kuiper Belt flyby would modify the orbit slightly, potentially setting up additional encounters that kept the object bound to the Sun's gravity at distances where solar heating remained minimal, and observation from inner solar system telescopes became extremely difficult. The trajectory looked less like a visitor passing through and more like an exploration mission designed for long-term study of the outer planetary environment. Energy efficiency analysis revealed that the perihelion and Jupiter maneuvers had been executed with precision that maximized scientific utility of the resulting orbit. The 47 meter per second delta V at perihelion, combined with the 12 meter per second Jupiter boost, created exactly the trajectory needed to tour the Kuiper Belt while conserving propellant for potential future adjustments. Random outgassing or natural gravitational effects wouldn't produce such optimal results. The trajectory planning implied either extraordinary luck in how natural forces happened to work out, or guidance systems calculating optimal burns to achieve specific mission objectives. Most troubling was what the trajectory said about 3I Atlas's priorities. If the object had wanted to escape the solar system quickly, it could have used Jupiter for a maximum energy slingshot that would have sent it outbound at higher velocity. Instead, it chose an orbit that kept it in our cosmic neighborhood for extended observation campaigns. Whatever 3I Atlas was, whatever controlled its motion, it apparently wasn't finished with our solar system yet. The tour of the outer planets and Kuiper Belt was just beginning. March 23rd, 2026 marked the official beginning of the Vera Rubin Observatory's Legacy Survey of Space and Time, the most ambitious astronomical survey ever attempted. The 8.4 meter telescope in Chile began its programmed cadence of scanning the entire southern sky every few nights, designed to detect transient phenomena from supernova to near-Earth asteroids. The survey's unprecedented sensitivity and sky coverage promised to revolutionize time domain astronomy across multiple fields. Nobody expected the revolution to start during the first week of operations. The automated detection pipelines identified 17 candidate interstellar objects in the initial 7 nights of survey data. Not marginal detections requiring extensive follow-up to confirm, but clear, fast-moving objects with trajectories suggesting hyperbolic orbits and extrastellar origins. The discovery rate was staggering. More interstellar visitors detected in 1 week than humanity had confirmed in the previous 8 years combined. Either the solar system was experiencing an unprecedented influx of visitors, or previous surveys had been missing the vast majority of objects passing through due to sensitivity limitations and inadequate sky coverage. Survey scientists immediately initiated follow-up observations to confirm the interstellar nature of these candidates and characterize their properties. Spectroscopy, photometry, and high-resolution imaging began within hours of detection for the brightest candidates. 3 of the 17 showed characteristics that made them immediate priorities for intensive study. All 3 exhibited geometric patterns in their dust distributions, similar to what Parker had photographed around 3I Atlas. The radial symmetries weren't identical. Each object showed variations in the number of features and their spacing, but the underlying organizational principle looked the same. 2 of the 3 priority candidates showed thermal signatures inconsistent with passive solar heating. The temperature distributions revealed hotspots that didn't align with solar illumination geometry, echoing the thermal anomalies 3I Atlas had displayed. 1 candidate showed periodic brightness variations with a stable 8.2-hour cycle, suggesting rotational stabilization, similar to 3I Atlas's transition from chaotic tumbling to precise spin. The patterns were repeating across multiple objects, indicating that 3I Atlas wasn't a unique case, but represented a class of interstellar visitors with shared characteristics. The size distribution of the detected candidates provided crucial context for understanding the population statistics. Unlike the 3 previously confirmed interstellar visitors, which ranged from hundreds of meters to potentially 5 kilometers, the legacy survey detections spanned from roughly 1 kilometer down to perhaps 300 meters based on brightness and assumed albedos. This matched theoretical predictions that smaller objects should vastly outnumber larger ones in any debris population, natural or artificial. The detection of numerous smaller candidates alongside rare massive specimens like 3I Atlas suggested that survey sensitivity rather than population scarcity had limited previous discovery rates. Most significantly, preliminary analysis suggested that objects showing geometric patterns and thermal anomalies represented a substantial fraction of all interstellar detections, perhaps 20 to 30% of the total sample. This wasn't a rare phenomenon or statistical fluke involving 1 or 2 unusual visitors. If the initial week's findings held up under detailed scrutiny, roughly 1 in every 4 or 5 interstellar objects passing through the solar system showed characteristics that strained natural explanations and suggested technological origins. Humanity wasn't just sharing the galaxy with 1 or 2 anomalous visitors. The space between stars apparently contained a population of objects that behaved nothing like natural cometary debris, and they were passing through our solar system constantly, mostly unnoticed until systematic surveys finally achieved the sensitivity to detect them consistently. The Vera Rubin discoveries triggered immediate diplomatic activity as space agencies and governments worldwide confronted evidence that interstellar visitors with apparent technological characteristics were far more common than anyone had imagined. How different nations chose to handle this information revealed competing priorities between scientific transparency, national security concerns, and international cooperation. The responses ranged from cautious openness to aggressive intelligence gathering, creating a fractured global approach to what was arguably humanity's most significant astronomical discovery. NASA maintained its classification posture, established after the October Parker observations. While acknowledging the Vera Rubin detections publicly, since those came from an internationally accessible facility, the agency refused to release detailed analysis of the objects showing geometric patterns or thermal anomalies. Official statements emphasized the preliminary nature of the findings and the need for extensive verification before drawing conclusions about origins or characteristics. Behind this public caution, NASA established a dedicated task force coordinating observations across multiple spacecraft and ground facilities, treating the interstellar visitors as potential intelligence targets rather than purely scientific phenomena. The European Space Agency adopted a more transparent approach, publishing preliminary data on several candidates detected by ESA facilities and encouraging international collaboration on follow-up observations. However, this openness came with notable exceptions. The October Trace, gas orbiter observations of 3I Atlas remained classified, and ESA member states received briefings under confidentiality agreements that prevented public disclosure. The split approach suggested internal debate between scientists advocating for transparency and security officials demanding caution until the nature of these objects could be properly assessed. China's response involved immediate activation of its Lunar Far-Side Radio Telescope Array. The facility, shielded from Earth's radio interference by the Moon's bulk, began systematic monitoring of known interstellar visitor positions across multiple frequency bands. Chinese space authorities made no public statements about what they were searching for or what they might be detecting, but the rapid deployment of resources indicated that Beijing took the possibility of technological artifacts seriously. Western intelligence agencies noted increased Chinese interest in expanding deep space monitoring capabilities and establishing orbital platforms for interstellar object tracking. Russia announced plans to resume deep space radar operations that had been dormant since the Soviet era, citing the need for improved tracking of objects passing through the outer solar system. The stated justification focused on planetary defense and asteroid threat assessment, but the timing and specific capabilities being restored suggested interest in characterizing interstellar visitors extended beyond protecting Earth from impacts. Russian officials privately approached several Western counterparts proposing data-sharing agreements for interstellar object tracking, proposals that generated lengthy negotiations about what information would be exchanged and under what restrictions. Japan's space agency began redirecting several astronomical satellites for dedicated interstellar visitor monitoring, while also proposing an international framework for coordinating observations and sharing data. The proposal included provisions for handling potentially sensitive discoveries, attempting to balance scientific openness with security concerns. Initial responses from other space agencies showed interest in coordination, but significant disagreement about classification criteria and information sharing protocols. The emerging pattern showed competing impulses toward both cooperation and intelligence gathering. Every major spacefaring nation recognized that interstellar visitors with possible technological origins represented information of strategic importance. But national interests and security concerns prevented the kind of unified global response that many scientists advocated. The result was a patchwork of overlapping observation programs, classified analysis efforts, and limited data sharing that left humanity's response to this cosmic phenomenon fractured along geopolitical lines rather than united by shared curiosity about our place in the universe. By April 2026, enough evidence had accumulated that serious scientific evaluation of technological origins for 3I Atlas and similar objects could no longer be dismissed as fringe speculation. Multiple independent lines of evidence, geometric patterns, thermal regulation, trajectory optimization, radio emissions, rotation stabilization, and spectroscopic evolution all pointed toward characteristics inconsistent with natural cometary behavior. The question facing the scientific community was no longer whether these observations were real, but what threshold of proof had been crossed and what explanations remained viable. The Galileo project, established specifically to investigate potential evidence for extraterrestrial technology, released a comprehensive analysis evaluating 3I Atlas against established criteria for distinguishing artificial from natural objects. The assessment examined 6 key characteristics that technological artifacts should exhibit: geometric organization beyond what natural processes produce, energy signatures inconsistent with passive environmental heating, trajectory modifications suggesting propulsion and navigation, stable mechanical states requiring attitude control, material properties indicating refinement or manufacturing, and information-bearing signals. 3I Atlas showed positive or suggestive evidence for all 6 criteria. The geometric organization criterion was met definitively by Parker's imagery, showing 6-fold radial symmetry maintained over weeks of observation. Natural processes occasionally create apparent patterns through coincidence or special viewing geometry, but sustained geometric precision across multiple observation sessions exceeded what natural mechanisms reliably produce. The probability calculations suggested odds of less than 1 in 10,000 that random dust distributions would maintain such symmetry purely by chance. Energy signatures clearly indicated excess thermal output beyond solar heating, with the 6.7-hour periodicity suggesting regulated internal processes rather than passive response to external conditions. The trajectory modifications, totaling nearly 60 meters per second of delta V across perihelion and Jupiter encounters, executed without detectable exhaust, met the propulsion criterion. The rotation stabilization from chaotic tumbling to precise periodic spin satisfied the attitude control requirement. Material properties remained the weakest criterion, with spectroscopic evidence suggestive but not definitive for refined metals. The enhanced nickel emissions and ionized metal signatures were consistent with but didn't conclusively prove manufactured materials. The radio signals detected by multiple facilities provided the strongest evidence for information-bearing transmissions, showing modulation patterns with statistical significance far exceeding natural radio source characteristics. Critics argued that extraordinary claims required extraordinary evidence, and while 3I Atlas showed unusual properties, none individually proved artificial origins beyond reasonable doubt. Perhaps exotic natural physics operating in interstellar objects could explain the observations through mechanisms science didn't yet understand. This position maintained scientific conservatism by requiring absolute proof before accepting revolutionary conclusions. Proponents countered that the cumulative weight of multiple independent anomalies, all pointing toward the same conclusion, constituted the extraordinary evidence that skeptics demanded. When objects show geometric patterns and thermal regulation and trajectory control and radio emissions and rotation stabilization and spectroscopic evolution simultaneously, invoking unknown natural processes for each anomaly separately became less parsimonious than accepting the single explanation that fit all observations, technological artifacts from non-human intelligence. The scientific community found itself divided not along traditional disciplinary lines, but by different philosophical approaches to evaluating ambiguous evidence. Some demanded smoking gun proof that would convince even the most skeptical observers before accepting non-human intelligence as an explanation. Others argued that the preponderance of evidence had already crossed reasonable thresholds for treating technological origins as the leading hypothesis. Both positions claimed to represent proper scientific methodology, revealing that the standards for accepting revolutionary conclusions remained contested even as the evidence accumulated. Accepting that 3-eye atlas and similar objects might represent technological artifacts raised profound questions about their origins, purpose, and age. The galactic archaeology paradigm offered a framework for understanding these visitors not as contemporary missions from active civilizations, but as ancient autonomous probes launched billions of years ago by societies that might no longer exist. This perspective transformed the implications from potential first contact with living intelligence to discovery of cosmic artifacts that had been drifting through the galaxy since before Earth's sun ignited. The timescales involved in interstellar travel made ancient origins almost inevitable. Even traveling at relatively high velocities of tens of kilometers per second, crossing the distances between stars, requires hundreds of thousands to millions of years. An object moving at 50 kilometers per second, fast by spacecraft standards, but modest for interstellar trajectories, would take 20,000 years to traverse just 1 light-year of space. The nearest stars to our Sun sit 4 light-years away, implying minimum transit times approaching 100,000 years for objects originating from our immediate stellar neighborhood. If 3-eye atlas came from stellar systems hundreds or thousands of light-years distant, as its arrival direction might suggest, the transit time could extend to millions or even billions of years. During such intervals, the civilizations that launched these probes could have evolved beyond recognition, collapsed through catastrophic events, or simply gone extinct through natural demographic processes. The probes themselves would become the sole remaining evidence of cultures that thrived when the galaxy was younger, autonomous artifacts carrying out programmed missions long after their creators disappeared from the cosmic stage. Self-repair mechanisms became essential for understanding how technological objects could function after such extreme durations. Natural degradation from cosmic ray bombardment, micrometeorite impacts, and thermal cycling would destroy any static technology over millions of years. Only systems capable of diagnosing damage and repairing or replacing failed components could maintain functionality across the timescales required for galactic-scale exploration. The geometric patterns and thermal regulation that 3i Atlas displayed might represent successful self-maintenance rather than recent manufacturing, systems that had been continuously operating and repairing themselves for time periods measured in geological epochs. The solar system as waypoint concept reframed 3i Atlas's passage through our planetary neighborhood. Rather than targeting Earth specifically, the object likely followed a trajectory sampling stellar systems across the galaxy, recording planetary architectures for purposes we could only guess at. Our Sun represented one stop among perhaps millions in a journey spanning the galactic disk. Von Neumann probe scenarios suggested the most unsettling possibility. If these artifacts could replicate using raw materials from visited systems, a single probe launched billions of years ago could have spawned countless descendants now populating the galaxy in numbers exceeding anything biological civilizations could achieve. The 20 to 30% of interstellar visitors showing technological characteristics might represent a self-replicating population that had achieved galactic ubiquity through exponential reproduction over cosmic timescales. This paradigm implied humanity existed in a galaxy densely populated with autonomous artifacts, relics of vanished civilizations whose technological descendants continued executing ancient programming. The implications stretched beyond first contact into questions about humanity's place in a universe where intelligence might be common, but often left only machines as lasting legacy, artificial archaeology drifting through space, carrying encrypted memories of cultures we would never meet. The demonstration that 3i Atlas possessed intelligent guidance fundamentally altered planetary defense calculations. Traditional asteroid assessment focuses on natural objects following predictable trajectories, allowing decades of advance warning. When objects can modify courses and respond to their environment with decision-making capabilities, the entire framework for protecting Earth required reassessment. Implications extended beyond immediate safety into questions about preparing for futures where not all visitors might be benign. Current detection systems were designed to find objects approaching on natural orbits. 3i Atlas demonstrated that some visitors could execute trajectory changes invalidating months of tracking data, potentially approaching from unexpected directions, or altering impact probabilities through deliberate maneuvers rather than natural perturbations. The 13-day warning problem highlighted inadequate response capabilities. If an object like 3i Atlas decided to target Earth, time between detecting a threatening trajectory change and potential impact could be measured in days rather than years. Current planetary defense concepts involve deflecting incoming objects or evacuating impact zones. Both strategies require substantial lead times that wouldn't exist if intelligent visitors chose hostility on short notice. Intent assessment became a critical challenge planetary defense had never addressed. Natural asteroids possess no intentions. Objects demonstrating guidance capabilities might have purposes ranging from scientific exploration to resource extraction to potential hostility. Distinguishing between these possibilities would require communication attempts and threat assessment protocols that didn't exist. Treating every intelligent visitor as potentially hostile would preclude scientific opportunities, while assuming benign intentions could prove catastrophic. International cooperation requirements reached urgency levels that geopolitical realities struggled to accommodate. Effective planetary defense would require coordinated global monitoring, shared intelligence, and unified decision-making. The fractured response to 3I Atlas revealed how far current cooperation fell short. Nations competed to gather intelligence rather than pooling resources, classified observations rather than sharing data, pursued separate analyses rather than coordinating assessments. Congressional hearings scheduled for June 2026 would address these deficiencies, evaluating whether existing programs required restructuring. Proposed measures included expanded deep space monitoring, development of rapid response capabilities, establishment of international protocols for assessing visitor intentions, and contingency planning for scenarios where communication failed. Budget implications were substantial, but remaining unprepared for maneuvering visitors seemed increasingly unacceptable. The philosophical question underlying all practical concerns involved whether humanity should view objects like 3I Atlas as threats requiring defensive postures or opportunities demanding open engagement. Current evidence suggested these visitors showed no hostile intent, passing through without approaching Earth closely. But absence of hostility to date provided no guarantees, and prudent planning required considering worst-case scenarios alongside optimistic hopes. April 26, 2026. 3I Atlas crossed beyond Jupiter's orbit, continuing toward the outer solar system, and Kuiper Belt encounters that trajectory analysis predicted. Ground-based telescopes tracked it until distance, and fading brightness pushed it below detection thresholds. The object that had dominated astronomical attention for 10 months gradually disappeared, carrying answers to questions humanity had barely begun formulating. The possibility that humanity was being observed transformed how we understood our cosmic place. If 3I Atlas and similar objects represented reconnaissance missions, then Earth had been under surveillance during the entire span of human civilization, without our awareness. Every achievement and catastrophe might have been recorded by silent observers passing through, their presence undetected until technology advanced enough to notice anomalies. We weren't discovering interstellar visitors so much as becoming aware of monitoring that had likely been ongoing for millions of years. The evaluation hypothesis offered less comfort. Perhaps these probes didn't simply observe but assessed, measuring civilizations against unknown criteria to determine whether contact was warranted. 3I Atlas's trajectory, its maneuvers, even transmitted radio signals, might represent evaluation protocols. Humanity's response could itself be part of assessment. The classification decisions, international competition, and fractured response might be telling whoever programmed these probes exactly what they needed to know about human readiness for broader cosmic participation. The ignored possibility remained most humbling. 3I Atlas might be aware of humanity without considering us significant enough for special attention. Civilizations launching self-replicating probes across galactic distances might view younger technological societies as interesting, but ultimately inconsequential. The solar system could be just another data point in vast catalogues compiled over billions of years, with Earth's biosphere rated as an unremarkable example of common processes. What remained certain was that humanity's cosmic isolation had ended not through radio signals, but through discovery of artifacts passing through our neighborhood. The galaxy wasn't empty wilderness. It was an ocean traversed by autonomous explorers, previously invisible, but now undeniable once we learned to recognize the signs. Every star system might host similar visitors conducting ancient missions, with technological debris from vanished civilizations far more common than the living societies that created them. The whistleblower who leaked Parker Solar Probe's classified imagery on October 31st, 2025, was never publicly identified. Internal investigations failed to determine who uploaded 17 gigabytes of restricted data through anonymizing networks. Several mission personnel resigned or transferred afterward, but no charges were filed. The silence suggested either authorities chose not to prosecute someone whose actions many viewed as serving public interest, or that the breach implicated individuals too senior to pursue. The scientific community's response evolved from shock to grudging acceptance that classification of astronomical discoveries represented dangerous precedent. Professional organizations affirmed that celestial observations should remain public regardless of implications. Several prominent researchers refused participation in classified projects, arguing secret science violated peer review principles. Others countered that national security justified temporary restrictions, creating divisions within astronomy departments. Public reaction proved more complex than anticipated. Initial speculation generated exactly the conspiracy theories classification was meant to prevent. But as more information emerged, public discourse matured into substantive discussions about humanity's cosmic place. Opinion polls in late 2026 showed majorities favored transparency, even if discoveries carried unsettling implications, suggesting populations were more resilient to extraordinary revelations than authorities assumed. Congressional hearings in June 2026 produced legislation establishing protocols for handling discoveries with potential security implications. The framework required classified observations be reviewed for declassification every 6 months, with scientific panels empowered to challenge unjustified decisions. The legislation didn't eliminate classification, but imposed oversight to prevent indefinite suppression. Final observations came from Hubble in early May 2026, capturing the object at nearly 6 astronomical units. Geometric patterns remained visible, though fainter. The stable 6.7-hour rotation persisted, suggesting whatever systems maintained. That spin continued operating. Then, 3I Atlas dropped below detection thresholds, becoming another faint point among billions, its secrets intact and its mission continuing unseen.